Hello, and welcome to the Supermicro Storage Summit. In this session, we're going to talk about scale-out storage for cloud environments. My name is Paul McLeod. I'm a product director here at Supermicro. And joining me today is Alan Johnson, a solution manager who basically focuses on some of our scale-out and scale-up architectures. Also will be Max Chung. Max Chung is on the Cloud Solutions Group, and he's going to talk about some of our partner solutions with our Linux partners. And then we have Gushar Gohad from Intel. Gushar is going to talk about some of the acceleration products that Supermicro and Intel have to offer. You know, these are things like Optane, you've probably heard of. And then finally, we have Wally McDermott from Scality. Wally is going to talk about the solution we're launching here at the Summit, which is Scality Ring, and this is utilizing our top loading servers and our Simply Double architectures. But before we jump into the sessions, let's have a look at a video that was created by Patrick Kennedy of Serve the Home.
This server next to me is the Supermicro Simply Double, and this server breaks a lot of molds. And what I mean by that is that the server itself has a couple features that are completely different than other servers in the Supermicro lineup. Now, the Simply Double server itself is actually a dual socket, second generation Intel Xeon Scalable platform, which we've definitely seen before. But in front, you can see this thing. And what this allows you to do is it allows you to have 12 3.5-inch hard drives and a 2U chassis up front, kind of like you would normally see, but then you can have a second set of these 12 drives in back. And why that matters is that you can pull this chassis out a little bit and you can pull these up and get access to hot swap these drive trays. And you might ask, hey, why do you have a system and why do I even want 24 drives in a 2U system? Well, it turns out that 2U is just a really popular form factor. It's good for cooling and space efficiency. And what you're going to see is that with the new second generation Intel Xeon Scalable processors, you actually can get 12 cores per CPU in some of the lower cost segments, so Xeon Silver, Xeon Gold. And when you have 12 cores, there are a lot of object storage applications that match number of cores to number of drives. And so if you have a 12-core CPU, that matches well with 12 drives. And if you have two, because you have a dual socket server, two 12-core CPUs, that matches really well with two sets of 12 drives, hence the 24 drive configuration in a 2U form factor of the Simply Double. So hey Paul, I've known you for years and you're the director of the Super Storage Group at Supermicro, and this is one of your products, and I think this is one of your best-selling products. So maybe you could just tell us you've had this on the market for years, it's really popular, so who are the types of customers and industries that really use this type of platform?
So really where it's really hit a mark is in media streaming online, right? The guys that need to have content at a moment's notice, you know the names. They use this because, again, they need a very large footprint of their content, and then there's caching options in the Simply Double line that allows them to put those very popular clips into a very fast storage. So we have a good tiered storage story with Simply Double.
Okay, thank you, Paul, for that. My name's Alan Johnson, and I look after a lot of our software-defined storage applications. So really what I want to do in this session is set the scene for the later speakers who will be talking more specific. My system is more general, where we really talk about some of the concepts that everyone else will be speaking about. So we're going to talk a lot about object storage. We're going to talk about cloud storage. We're going to talk about scalability, and a lot of these terms and concepts tend to overlap quite a bit. But before we talk about why the need for object storage, we can just look a little bit about, I guess, the existing storage today. I don't want to say the past, because some of these protocols are still very dominant today and will continue to be for quite a while. But traditionally, we've had block storage, and block storage is really just handled as a sequence of logical blocks on discrete disk drives as well. We really come back from a lot of legacy terms here. We talk about sectors, we talk about tracks, and really these have no counterpart with solid state media today. Nevertheless, we will emulate them to make sure that everything still works. With file systems, we often have a very deep nested hierarchical structure as well. And all these things contribute to problems with scalability. With discrete devices, you have to know where everything is. You have to mount them on different mount points. You really have to have a fairly intimate knowledge of the system. Whereas with object storage, we present just one big namespace. So you can just access the data using a fairly flat type of query, a bit like what you do with Google. You can use HTTP to just go and retrieve your data. So it's a lot more natural with today's way of thinking as well. And the idea behind the scalability, we can scale our systems locally across devices, across servers, or we can have data center zones, or we can even have geographical regions. So again, that's all transparent. It's just one big lump of storage for everybody. The other term that we're going to talk a lot about is structured and unstructured. You'll hear this term a lot about objects being unstructured. Well, traditionally, data tends to be very well handled. You have over on the right-hand side a number of database fields, which are the vertical columns, and then you have records, which are the horizontal rows. And a lot of the data lends itself very well to this kind of thing. So what we do is we take the data, we normalize it, as the term is, and then we can very easily perform queries on various fields and things like that. But when we have objects, we really don't have this kind of nice data structure. You have things very diverse. You can have a PDF document, which is just really a bunch of text. You can have video files, which you might want to look at. You can have JPEG pictures as well. So you really can't divide them up like this, but instead, these objects will have their own associated metadata. So you probably notice if you take pictures with your phone camera, it'll have things like the geographical location, the date that the picture was taken. So you can actually search on these things using these tags as well by themselves. So they're really self-contained, and it's probably a more natural way of doing things as well. So this object storage is usually vast. We talk about big data and data lakes, and a lot of this is held in all these various servers, and they can be held either maybe off the customer's own premises with somebody like a discrete data center or Amazon or Microsoft Azure, all these ways of doing it. Or you may want to decide, well, I'm going to actually do this kind of thing. I like it, but I have some concerns maybe with the security and maybe the costs and things like that. So what I'd like to do is have one of these cloud systems set up where I can store all my objects, but I'd like to do them on my own premises. And that would be an example of a private cloud. And quite often, many people have private clouds and public clouds, and this would be termed a hybrid cloud. So quite often, one size doesn't fit all. What I want to do then is just to have a look now at one example of some of this software-defined storage where we can implement storage for these cloud systems. And one that's fairly common today is Ceph. So just to talk a little bit about Ceph, it's fairly unique in that not only does it cover the objects that we talked about, but it still has the support for files and blocks as well. And many people will use it with some of those various roles as well. Ceph seems to be pretty well the de facto standard for Kubernetes and OpenStack, as well as back-end persistent storage. So it is very popular out there, and it does provide gateways for Amazon S3 and OpenStack Swift as well. So that's within the architecture of Ceph. Looking a little bit closer, this picture is unashamedly taken from the Ceph website, but they give a nice little picture of the architecture there. And you can see a couple of different types of servers. There's things called MONs, MDS, OSDs. Well, the MON is short for the monitor node, and really the monitor node is the overseer. It has an understanding of the Ceph map, who belongs there, what members are there as well. The next one is the metadata server, and this is only used for Ceph FS, the file system. What happens is with the objects and the blocks, things are handled a little bit differently as well. The other thing you don't see there is the gateway nodes. So you can have a gateway node for the Amazon S3 interface, which we talked about earlier as well. And then you'll see a couple of other things there. Like the networks, you have a public network which everybody communicates on, and then you have a private backend cluster network which can be used for replication between the object storage devices. So when we're sizing these, usually the one that causes us the most input really are the OSDs. So when we want to size the Ceph system, we have to take into account the replication scheme, whether we're doing a two-way replication, three-way, or whether we're using erasure coding, which is much more like a RAID system as well. So again, this is just looking at the same thing. We don't have to have discrete servers. We can converge them together. And quite often today, a lot of these roles will be converged. So you won't have a discrete server taking on a particular role. You can actually combine these as well. So we mentioned a little bit about the network, and that can be important when you're doing things like replication because it can offload some of the activity from the front side of the public network. So when we test these systems, we're really looking to do three types of things. We want to optimize for cost. Obviously, I don't want to do this system with the most expensive component, like the highest level of a CPU, if we only get a very small increment in performance. So I don't want to double the cost for maybe a 2 or 3% performance increase. So what we would do is typically we'll incrementally test these. We'll go with maybe the highest level CPU, see how performance is. We'll monitor things like CPU utilization, and then we might step back a bit, or equally we might start at the bottom and step forward. So we want to make sure we have a good blend of cost so that we come up with a solution that can be practical as well. The next parameter we look at is performance and capacity. So we can capacity or optimize one of these systems. So if it's for archive, where maybe we're looking at throughput and IOPS aren't really a concern, then we can usually use one of our larger bay counts, perhaps using HDDs. But once we get into performance, then we really want to go with perhaps solid state media, NVMe being a good example of that as well. And these will be much better for high IOPS type systems as well. And then, of course, we want to look at resilience. How many of these nodes are we going to have? What sort of replication scheme are we going to have? Should we use erasure coding? We have to also take into account, is that going to contrast against the performance and give us a hit? So there's a number of different metrics that we have to take into account as well. So with that, I'd like to pass it over to the next speaker, who will go into a little more detail and talk about some of the practical side of things. So thank you very much.
Hello, everybody. Welcome to the session on scale-out storage solutions with Supermicro. Now that we have learned what scale-out storage is from a technical point of view, and how it can be deployed in a public cloud or private cloud or in a hybrid cloud should there is a need. Here we are going to take a look at the Ceph reference architectures we have built with our software vendor partners and how they enable our customers to leverage scale-out storage solutions to solve their data storage challenges in the age of data explosion. Here are the links to the reference architectures we have worked and built with our software vendor partners. Our software vendor partners include Canonical, which is a parent company of Ubuntu Linux, and Red Hat, which was acquired by IBM last year, and also SUSE, which has a large customer base in EMEA and APAC. All reference architectures are built with systems certified by our respective software vendor partners. This is a very important aspect of any solutions for any customers, as all customers, they will want to get software support packages from our partners. Without using certified systems in a solution, our partners' field engineering team just won't be able to provide technical support when needed. This drawing shows our overall solution deployment and go-to-market strategy. We have 5 stages in the process, which can be further divided into pre-sales activities and post-sales activities. We start with education and the documentation. In this stage, we publish our reference architectures built with respective software vendor partners on our Supermicro website. And those web pages also contain brochures, white papers, and the benchmark test results. In the design and solution stage, we then help customers design and customize self-storage solutions based on their use cases and requirements. After we sell our solution, we help customers deploy software on the system, including OS installation and configuration, switch provisioning according to the network design, and bring out stack and services. Finally, for the ongoing management and support for the storage solution, we rely on our partners to provide such services. This diagram shows our standard Ceph reference architecture. This is the foundation of our Ceph solutions, so we are going to spend a little bit more time here. On the top, we have 4 switches sitting on top of all servers. 2 of them are data switches, which are used to provide connectivity among servers within the rack and for east-west type of traffic. This is also used to provide connectivity between the clients outside of the rack and the servers within the rack. This is what industry refer to as north-south traffic. We have 2 of them to provide node redundancy as well as link redundancy. They are acting as a single logical switch to all systems within the rack with a feature called MC-lag, multi-chassis lag. If you are more familiar with Cisco's terminology, the feature is called VPC, Virtual Port Channel. Each server within the rack has a bounding link to both data switches. In the case of a link failure or a node failure, the whole storage cluster will continue to function and provide storage services, but with a reduced network bandwidth. Same type of redundancy is achieved on the management network with 2 management switches. This management plan is for managing all systems within the rack, including switches and servers. Below the switches, we have 6 1U systems serving the roles of what we call infrastructure nodes. These nodes don't actually provide storage services to the clients, but they provide an overall infrastructure to the Ceph solution. Among these infrastructure nodes, we have 1 admin node, which is used to run administrative work, such as provisioning the servers and applying security patches to those servers. And we have 2 gateway nodes, which are used as storage gateways to expose storage services to the client. These storage services including object storage interfaces such as Amazon S3 based RESTful APIs and Swift compatible APIs. Below the gateway nodes, we have 3 Ceph monitor nodes. A Ceph monitor maintains a master copy of the cluster map, and we have 3 of them here to provide high availability and then maintain a storage cluster coherence. Finally, we have 4 OSD nodes here, and these nodes are the actual servers that provide actual storage capacity to the clients. We recommend a minimum of 4 OSD nodes for any production type of deployment. Now, this table shows the systems that we have validated to be used in SUSE-based Ceph solutions. We have 5 options to fit different use cases. We have all flash, high performance, balanced, storage optimized, and extra large storage. In this table, we also have recommended servers to be used in each of the options, as well as drive sizes, interfaces, and form factors to be used. We also outline the data network interfaces to be used in the table. Please note this table is not something absolute. We use this table as a conversation starter and as a template to work with customers to build customized storage solutions that will fit their needs. This diagram shows our canonical-based reference architecture. This is a bit different from the one that is SUSE based, as this is an OpenStack and the SUSE combined and the Ceph combined HCI solution. HCI means hyperconverged infrastructure. Similar to SUSE-based Ceph solution, we have redundancy on both network for data and for management. Another major difference here is there are 3 infrastructure nodes here that are being used to run administrative work for this OpenStack plus Ceph solution. A lot of customers of ours, they do like this kind of design, as the solution will be able to scale out horizontally in terms of compute power as well as storage capacity. Here's a list of Canonical certified systems. We use SYS 6019U TN4RT as infrastructure node across all Intel-based options. And then we use SYS 6029U TR4T for both performance and the value options for cloud nodes. The major difference between performance and value options are CPU core count, amount of memory, and the type of storage being used in a cloud node. Performance option has more CPU cores, more memory, and uses SSD as primary storage. Again, this is just for reference and as a conversation starter. Okay, now let's take a look at the Red Hat-based solutions. Red Hat Ceph reference architecture is very similar to SUSE Ceph reference architecture. Based on customer storage requirements, we can design and custom build a complete end-to-end turnkey storage solution. The diagram shows 3 monitoring nodes on the top, which also serve as an admin node and the dual gateway nodes. And the rest of the nodes are the OSD nodes, which provide extra storage function to clients. The diagram only shows the graphical representation of our Red Hat-based solutions. If you go to our website, you will be able to see more details options available. This diagram shows OpenStack plus Ceph reference architecture that is based on Red Hat. And this is a very common scale-out storage deployment scenario to use Ceph as OpenStack backend storage. In this diagram, we see a very similar networking design to Canonical's HCI reference architecture. We have both data switches and 2 management switches to provide connectivity among servers and for clients to access the storage cluster. Ceph monitor nodes and OpenStack controller nodes reside on the same physical servers. Then we have compute nodes to provide compute function and the Ceph OSD nodes to provide backend storage function. This concludes my presentation. Thank you all for your participation. I hope this is informative for you. We will have a Q&A session after next presentation. Thank you.
Thank you, Max. Almost over a decade that I've been at Intel, I've had the unique privilege in working with largest CSPs, enterprises, and telcos, co-engineering solutions for current and future workload demands. Today, I'm going to discuss what Intel believes is happening in the scale-out storage world, our involvement with Ceph in particular, and how we are working together with the partner and customer ecosystems in shaping next generation of storage technologies. Data center deployments have been based on 3 data storage paradigms, as Alan covered previously. Today, we'll focus on scale-out storage and discuss opportunities that are arising with the introduction of new storage and memory technologies, such as the Intel Optane. Scale-out solutions using object storage paradigm uses a flat address namespace that is virtually limitless. Object storage thus makes a perfect solution for scaling massive growth of unstructured data. Amazon S3, for instance, stores more than 2 trillion objects, and Facebook Haystack stores 1 trillion photos, both hundreds of petabyte scale. Now, object storage has been in development for years. 5 years ago, this is what we have talked about. In the cases that I just described, object storage was first conceived as a simplification to make storage more scalable, reliable, and lower cost. It was used in archive workloads. The trend is moving, though, towards high-performance data lakes. So this is where we are today, especially with CSPs. Data lakes at the CSPs are just more than archive or data dump. Decoupling data from the application enables an entirely new paradigm for data management. S3 Select serves as a great example. We have called out relevant Intel technologies here that are applicable for edge, core, and cloud, including some of the instruction sets that we have added for machine learning acceleration or storage function acceleration, such as erasure coding and crypto. We'll get into the details as we go along here. Now, let's take a moment and acknowledge a few trends that have emerged in the storage technology space. NVM Express and NVMe fabrics have begun to reach mainstream, and computational storage has become a recent topic of conversation and technology exploration. This is a new opportunity and one we are going to keep our eye on as it develops. Next, let's take a look at the memory and storage hierarchy over time, one that has existed since the dawn of computing. The job of this hierarchy is to provide data to the CPU quickly and store entire data set at a reasonable cost. At the top of the hierarchy, you have high cost, high performance DRAM. And as we walk down the pyramid, the target is higher capacity for data storage. But as we get to the bottom, we get further away from the CPU in terms of latency and bandwidth. As the dataset sizes increases, the top cannot hold everything we need and creating a capacity gap. And then at the bottom, we have a cost performance gap that exists between the low cost hard drives and TLC SSDs, which are higher performance enterprise drives. Intel is introducing new layers that are based on 3D Crosspoint Optane and QLC technologies to fill these gaps. These new layers will allow us to deal with increasing dataset sizes and have enough data closer to the processor to strike a balance between capacity and performance. This slide shows why Optane technology in particular is going to be important for the foreseeable future. When we look at the IOPS density or the IOPS per terabyte metric, which is very important for cloud service providers in making their infrastructure decisions. As drive capacities are growing up, NAND SSDs are not able to keep up their performance, which is causing IOPS per terabyte to potentially reach that of hard drives in the 2024 and timeframe and beyond. NVM Express and PCI Gen 5 will help, but it will fast reach end of the benefit as we go along here. Optane changes all of that. Optane has huge performance upside, which means it can saturate even PCI Express Gen 5 bus, and we see that continuing into the future. So from a IOPS per terabyte perspective, fast storage and capacity balance, Optane makes it a critical media for the future. Next, let's take a look at Intel technology at all layers of a scale-out solution. We have Xeon processors that power processing I/O and data services for your storage servers. You can take I/O bandwidths to new heights with Intel Ethernet adapters with up to 100 gigabit networking, which is especially important in STS solutions where data is distributed across nodes. These NICs support advanced features such as application device queues and also RDMA protocols like IORP and RoCE for high performance networking in STS solutions. Let's look at these technologies through a Ceph lens now. Intel Data Center family of SSDs use the NVM Express interface for performance. This family is built with data integrity, drive reliability, and performance consistency that you would expect from Intel. An example Ceph configuration could use Optane SSDs for metadata and caching and pair that with Intel QLC SSDs, which are basically the first on the market to offer 4 bits per cell NAND technology, which makes it really appealing from a cost and capacity perspective, potentially replacing hard drives, which could be used for your data tier. And make no mistake, Intel software is making its presence felt with huge performance gains. Our open source offerings like SPDK ISIL or OpenCAS framework have shown significant benefit with Ceph small block IO performance. Some of the instances are shown here where OpenCAS has delivered 500% performance improvement with caching, And SPDK has delivered double-digit performance gains for small IOs with Ceph. Now let's talk about Intel's contributions to the Ceph ecosystem and our collaboration with Supermicro. We have played an active role in the Ceph community over the last 7 years, be it customer collaborations, optimizing specific Ceph deployments, creating joint reference architectures with OEMs such as yourself, ISV partners, and nevertheless, bringing new functional and performance features to Ceph Upstream. We have shown some key workload examples that we have helped bring to Ceph over the years. We do want to make a very special mention of our partnership with Supermicro. We have co-developed workload optimized reference architectures that we are only looking forward to taking further. We really treasure this relationship. And lastly, here's a timeline of our contributions to Ceph. We have had a focused development effort around Ceph over the years that is focused on adding features and performance to Ceph. Intel is now the top 3 contributor to Ceph, only behind Red Hat and SUSE. I would like to call out our efforts around client-side and server-side caching, which may be very relevant to your CSP and enterprise customers. And also the high-performance Crimson OST project, which we helped started a couple of years ago, both focused on bringing the best of NVM Express and persistent memory technologies to Ceph. With that, I hope I was able to underscore Intel's holistic view on storage architecture evolution through innovation in hardware, software, and solutions. Thank you for your time. Now, I would like to hand it over to Wally.
Hi, my name is Wally McDermott. I'm Vice President of Strategic Alliances here at Scality, and I'm responsible for our worldwide resale relationship with Supermicro. If you're not familiar with Scality, we're a leader in the software-defined petabyte scale storage market. We're a global company founded in 2009 with offices throughout the world. We have hundreds of global customers who are some of the world's largest enterprises and most recognizable brands. And these customers trust Scality with one of their most valuable assets, their data. Data is really key to your business, and it's what allows you to serve customers better, faster, and with new services. Many of the modern applications your business uses or is building today create what we call unstructured data. So think of videos or document management systems, anything in the autonomous driving space, maybe medical imaging. Unstructured data doesn't follow a simple pattern. It's always different, and it can be very, very large. Today, 80% of the data in your organization is unstructured data, and it's growing 10 times faster than more traditional structured data, like you might find in a record management system like a Salesforce. So as your business must deal with petabytes and petabytes of unstructured data, you need a storage platform that was purpose-built to manage massive data growth. Scality Ring is just that. Ring is a software-defined scale-out storage platform that runs on Supermicro servers for petabyte scale capacity and performance. Ring can scale from 200 terabytes to hundreds and hundreds of petabytes. It's a very highly resilient and reliable platform that can protect your data from the loss of a disk, a server, and even an entire site. Because Ring maximizes the hardware resources on which we run, over time we deliver a very low TCO, cost-effective storage platform. Ring can be replicated across 2 sites and even stretched across 3 sites to provide you geo-redundant data protection. And again, if you lose an entire data center, Ring still allows you to access your data. And last but not least, we integrate with and can manage data not only across on-premises Scality Ring, but also all of the leading public cloud providers. Ring is a highly flexible storage platform that supports many concurrent use cases. We support the Amazon S3 Object API for use cases such as cloud and edge solutions, as well as big data and analytic use cases such as Splunk. But Ring also has a scale-out file protocol support for NFS and SMB, so we can support use cases in the data archive and backup space, as well as for specific verticals like medical imaging and media and entertainment as well. The benefit of Ring is you have a single storage platform that can support many, many of your applications, which further reduces the TCO over time. In our partnership with Supermicro, Scality and Supermicro have designed a solution that comes in two base configurations, one built for high performance and throughput, and another built for higher capacities. Both of these platforms include the native file and object support that I mentioned before, so NFS, SMB, as well as the Amazon S3 API. With this solution, customers can start fairly small with as minimum of a 3-node configuration, and that configuration can be either a half populated or fully populated with drives, depending on what your plans for future expansion are. And when it does come time to expand the platform, you can either do that with turnkey drive 6-packs or a more customizable expansion service. So now let's spend a couple of minutes talking about a Supermicro and Scality case study. A customer, a federal civilian agency, had a requirement to build a multi-site storage platform that was capable of scaling well beyond 30 petabytes. Today, this customer is running Ring and Supermicro servers, 30 to be specific, across 2 different sites, currently at 15 petabytes of data in the Ring and growing. This architecture and platform provides not a single point of failure and allows them in the future, as Supermicro releases denser, faster, cheaper hardware resources, to integrate those resources into Scality Ring without any downtime for maintenance. Over the years, Scality has multiple times been recognized by an industry leader, by IDC and Gartner. We've been a 4-time leader in the Gartner Magic Quadrant for object storage, and Gartner recently ranked us #1 for hybrid cloud use cases. Scality has also been a leader every single year that the IDC MarketScape report has been published. Thank you very much for your time today. If you'd like to learn more, you can go to scality.com/partners/Supermicro or email us at sales@scality.com. Thank you very much for your time.
Learn more at supermicro.com, powered by Intel.